Okay, let's talk about section 3.2. We already discussed the limit. If we want to find a generalization of limit, we will have a one-sided limit and a limit at infinity. That's another part. One-sided limits and limits at infinity. Limits at infinity. Okay, so the one-sided limit sometimes comes from a natural question. For example, if we have function fx equal to square root of x minus 1, we know that this function has domain x greater than or equal to 1. So this is a 1. The graph is like this. And then when we talk about the limit at 1, we can only allow x approaching 1 from the right hand side. Because for function makes sense, x has to be greater than or equal to 1. So it's from right hand side. So this is a one-sided. It's a left hand side, the right hand side, or possibly we can change the function together, the left hand side. Okay, right hand side or left hand side, depending on the problem. Right? So this is the natural way to introduce so-called one-sided limit. Okay, so let's see the definition. So let A be real. Okay. First, a real function f is said to converge to L as x approaches A from the right. Okay, it's like this, from the right. If and only if f is defined on some open interval I with left-hand point A. Okay, so you see here, this 1 is the left-hand point of this interval. That's the left hand of the interval. Left-hand point A, and for every epsilon greater than 0, there is a delta greater than 0. Okay, this delta depending on what? On epsilon, on f, on I, and on A. In general, I'm not saying it always depend on this, but in general, it depending on all the information you mentioned before it, such that A plus delta belong to I, so you cannot exceed the domain, and x is on the right side of A, but close to A implies absolute value fx minus L is less than epsilon. So this part is always ops value. So this part has nothing to simplify. The simplification comes from here. So x should be on the right side of A. So x is greater than A. And x is close to A, so x is minus A is less than delta. Okay? This, in the textbook, they gave the notation 2, the second condition. In this case, we call L the right hand limit. The right hand limit of f at A. And denoted by the following thing. You can write like FA plus. It's just notation in this textbook. This one is not a standard notation. This is just a notation in the textbook. By definition, it's equal to L. By definition, it's equal to the limit fx, x approaches A, plus, this is a standard notation. The right hand limit, this is standard notation. This one is just notation. It's reasonable. It is used, but it's not a commonly used one. Okay, in some books you will see this, but this one, all the mathematicians understand this. Okay, right hand limit. Counterpart, we will have the left hand limit. So the second, a real function f is said to converge to L as x approaches A from the left if and only if, okay, that is the right, from the right, this is from the left, if and only if f is defined on some open interval with right endpoint A, and for every epsilon greater than 0, there is a delta greater than 0. Again, in general, depending on epsilon I f a. Okay, in general, depending on epsilon f I a, such that first a minus delta move to the left, minus a minus delta still belongs to I, and a minus delta less than x less than a. This is on the left hand side, so it's the left limit. Okay, left hand limit. This implies ops value fx minus L is less than epsilon. Okay. Okay, so in this case, we call L the left hand limit of f at A, and denoted by FA minus. Here's FA plus. This is FA minus. This L is the limit x approaches A from left hand side fx. So again, I emphasize we use this widely. This is a left hand limit. Okay, so we have a right hand limit and left hand limit together, from right or from left. Sometimes, for example, for this function, if you talk about the limit at 1, so you can only talk about the right limit because the definition, the domain of f is on right side. But if you talk about any other point greater than 1, you can talk about the right limit, and you can also talk about the left hand limit. Okay, so it depends on how your function define. Okay, example. First, fx is piecewise defined function x plus 1 when x is greater than or equal to 0, x minus 1 when x is less than 0. For this piecewise defined function, if we consider x approaches 0 from right hand side fx, you see, whenever we talk about the one-sided limit, you only care the expression on the corresponding side. This is a right hand limit, so you consider x greater than 0. So the formula is x plus 1. Okay, so even though fx is equal to x minus 1 when x is negative, but it's useless for this computation. Here we require point from right hand side of 0. We require x positive. And this is equal to 1. So the right hand limit at 0 is equal to 1. Similarly, the left hand limit when x approaches 0 from left side, x is negative, so you are going to use this expression x minus 1, and x is 0, this is negative, right? So that's the way to define the limit. And of course we can see that when you allow x approaches 0 from right side, you get a positive 1. You allow x approaches 0 from left side, you get a negative 1. So there's no limit at 0. Does not exist, because if you want the limit exist at 0, you have to say no matter from left side or from right side x approaching 0, the value of fx will approach the same number. But here they approach two different numbers, so the limit itself does not exist. Okay, so right hand limit, left hand limit are two weak versions of the limit. They only consider one side, but limit itself, it considers two sides. Okay. Okay. Like what this theorem emphasize or demonstrate, actually we have the following theorem: that f be a real function, then the limit fx, x approaching a, exists and equals L if and only if L is the right hand limit is the left hand limit. Okay, if this is correct, the right hand limit is equal to the left hand limit is equal to L, then the limit itself is equal to L. Okay, Okay, now let's prove this. This is if and only if, so we have two directions. So here, first, we assume that the limit f(x) x approaching a equal to L. Okay, so we'll assume this one. And we're going to show the right-hand limit and left-hand limit are both L. Okay, this concept means for every epsilon greater than 0, there exists L greater than 0 such that x minus a less than delta implies absolute value f(x) minus L less than epsilon. That's the precise definition of a limit, epsilon delta definition. Okay, then this one, if you remove the ops value, it is equivalent to x minus a is between negative delta and positive delta. Okay, so you add a for all three sides, you will get x is between a minus delta and a plus delta. Okay, this is still the equivalence. And x is not equal to a. So this implies this is not equivalence. This implies x, well, x is between a and a plus delta f(x) minus L less than epsilon. And when x is between a and a minus delta, this is also ops value is less than epsilon. Correct? Yeah. So the first one implies the limit, the right-hand limit exists. The second one implies the left-hand limit exists. Correct? So this is a right hand. This is a left hand. Okay? So that's the proof from the existence of the limit to the existence of a one-sided limit. And they share the same delta. They share the same delta. Okay? Then the other direction. Second, assume the right-hand limit is equal to the left-hand limit is equal to L. So two one-sided limit exist and equal to each other. Then you have two limits actually. So for every epsilon greater than 0, there exists a delta 1 and a delta 2 greater than 0 such that the right limit is L, means x between a and a plus delta 1 implies ops value f(x) minus L less than epsilon. And the left-hand limit is L, so x is between a and a minus delta 2. This implies f(x) minus L is less than epsilon. For the same epsilon, you have delta 1 and a delta 2. Then this time, we choose delta to be the minimum of delta 1 and delta 2. Delta 1 and delta then x minus a less than delta implies x is between a and a plus delta 1, and x is between a minus delta 1 and a. This condition will imply both, and both imply ops value fx minus L less than epsilon. So from here, you get this. For every epsilon, you find the delta. Hence, the limit fx x approaching a is equal to L also. Okay, so you just choose the minimum among those two deltas, delta 1 and the delta 2, and that's enough. Whenever you have finite many, you can always choose a minimum. If you have infinite many, this minimum may be 0, that it does not satisfy the condition. Okay. Okay, so this is a natural definition from the some example, like the function is only defined on one side of a point. How do you calculate the limit from one side? And also we have a equivalent characterization about the existence of the delta of the limit. You talk about limit from right hand side, you talk about limit from left hand side. If they equal to each other, the limit itself exists. Okay, another thing, okay, this is the end of the proof. Another thing we want to study is the limit at infinity and the negative infinity. So when x approaches infinity, when x becomes larger and larger, or x approaches negative infinity, when x becomes negatively larger and larger. For those two cases, you see here, you can only approach positive infinity from the left hand side, and you can only approach negative infinity from right hand side. So those two concepts are very close to the one-sided limit. You are always on one side of the target point. But this part, delta is not, infinity is not a point. All right, so we're going to define the limits at the infinity. Okay, so we say that the limit, well, let me see. We say that fx converges to L as x approaches infinity if and only if let me clean my name. If and only if there exists a number c positive such that from c to infinity, this whole open interval is contained in the domain of f, and given epsilon greater than 0, there is in capital M in a real set such that x greater than capital M whenever you have a point, here's a capital M. Whenever you have a point is on the right side of capital M, implies ops value of fx minus L is going to be less than epsilon. Okay, it's going to be less than. Okay. This is the definition, and we denote it. We write or denote. We write x approaches infinity, fx. The limit of fx is L. Okay, so first of all, let's see here. First, the domain of f should covers almost all the right part. From certain point, C, the domain should contain this part. You do not have missing point. And second, what is the neighborhood of infinity? What is the neighborhood of infinity? You see here, if you have a point, two-sided neighborhood is like this. One-sided neighborhood is like this. Okay, but for the infinity, its neighborhood should be from C to infinity. Any part like this will be the neighborhood of infinity. So when you say a point is approaching infinity, just means that point becomes bigger and bigger, larger and larger. So that's why we require x is greater than some sufficiently large number m. When x is sufficiently large, fx is close to L. Okay, fx is close to L. So that's the definition. Okay, and this is the limits at the positive infinity. Let's write down the limit at the negative infinity. Okay, so fx approaches L as x approaches negative infinity if and only if there exists a C positive such that negative infinity C belongs to the domain of f and epsilon greater than 0, there is an m belong to the real number such that whenever x is less than m, it implies ops value fx minus L is less than epsilon. Okay, so this time negative epsilon, negative infinity is here. This is m, this is a C. So it goes this way. X is here. And we write the limit fx, x approaches negative infinity, is equal to L. Okay. And those two are called limits at infinity. Limits at infinity. And there are a similar concept called infinite limit. What are the infinite limit? For example, y equal to 1 over x. For y equal to 1 over x, when your x approaches 0 from right hand side, then you can see that the value will becomes bigger and bigger. So we will see that when x approaches 0 from right hand side, the limit of 1 over x is infinity. So that's an infinite limit. Okay, infinite limit. Limits at infinity, there are only two limits at infinity. Positive, negative, and positive. The limits at the positive infinity and the limits at the negative infinity, they're just two types. But infinite limits, there are 4 types. You see here, this is 2 types. Right limit is positive infinity. Left limit is negative infinity. So 2 types. Or the other way, right limit is negative infinity. Left limit is positive infinity. This is the other 2 types. So together there are 4 types of infinite limit. We are going to just write one, and you can write the other 3 types. Okay? So let's see. We say that fx approaches positive infinity as x approaches a from right hand side. Let's see one-sided first. Actually, there are more than 2 types. There are more than 4 types. There are 6 types. Or this way. And this way. Yeah, there are 6 types. Here, let's talk about this type, this one. So fx approaches positive infinity as x approaches a from right hand side, if and only if there is an open interval I with left endpoint A, with left endpoint A, such that and for any epsilon greater than 0, there is not epsilon, m. For any m greater than 0, there is a delta greater than 0, such that when x is close to a from right hand side, it implies fx is greater than or equal to this m. Okay? So when x is close to a, fx can be bigger than any pre-selected m. Then we write, this is the definition, then we write the limit fx, x approaches a from right hand side, is positive infinity. This is the situation. You can use this definition to write down the other 5 types of infinite limit. Other 5 types of infinite limit. After you get those limits at infinity and the infinite limit, we can get a combination of a infinite limit at infinity. Okay? So we have infinite limits at infinity. What is the infinite limit at infinity? For example, we can have limit approaches positive infinity, fx equal to positive infinity, if you let fx equal to x. Or the limit x approaches positive infinity, fx is equal to negative infinity, fx is negative x. Or limit x approaches negative infinity, fx is negative infinity. This is still the example fx is x. Or the limit x approaches negative infinity, fx is a positive infinity, The example is negative x, fx equal to negative x. Okay, so there are 4 types of infinite limits at infinity. Infinite limits at infinity. So it looks like this way, or this way. Okay, this is the first one. This is second one. Sorry, this is the first one. First one. This is the second one. This one, negative infinity, negative infinity. This is the first one. This is the second one. Okay. So once we understand the infinite just means it will be sufficiently large or sufficiently negatively large. Then we can write the stuff in terms of epsilon delta or capital M. Or capital M. Okay. So let's use one example to demonstrate. So we're going to prove the limit x approaches 0 from right hand side, 1 over x is infinity, past infinity. Okay, so let's see. We show that proof for any m greater than 0. We need 1 over x should be greater than m, right? 1 over x should be sufficiently large. And then you flip that, you go x is less than 1 over m. Of course, it's greater than 0. We assume this x is from right hand side. Okay, so just choose delta be 1 over m. For x greater than 0 and less than delta, it's a 0 plus delta. 1 over x is going to be greater than m. 1 over x is less than 1 over delta, is greater than 1 over delta, is greater than m. So, by the definition, the limit x approaches 0 from right hand side of 1 over x is past infinity. So this is one thing, and the same example, we can show that when x approaches infinity, 1 over x has limit 0. When x approaches infinity, 1 over x has limit 0. Okay, so how do we prove that? Given any epsilon greater than 0, we need 1 over x minus 0 less than epsilon. Okay, x approaches infinity, x will be positive. X approaches infinity implies x greater than 0. So it means 1 over x is equal to up's value 1 over x is less than epsilon. So flip to side, we will get x is greater than 1 over epsilon. Right? Flip this inequality. X is greater than 1 over epsilon. And choose m be 1 over epsilon. Choose m be 1 over epsilon. And for any x greater than m, 1 over x is going to be less than epsilon. And this is exactly what you need. And hence, by the definition, the limit x approaches past infinity 1 over x is equal to 0. Okay? So this is the example, a simple example about all the extended limits. So far we have many concepts about the limit. If you have the first one is the regular limit, two-sided, And then at the beginning of today's class, we have one-sided limit from right side, from left side. After that, we studied the limit at infinity because if infinity is here, we are always on the left side. If negative infinity is here, we are always on the right side. Okay? And then we study the infinite limit. So here, the function will approach positive infinity, or the function will approach negative infinity. We have infinite limit. And we also have infinite limit at infinity. Infinite limit at infinity. It's like this. And this example is just give us the simplest way to, the simplest demonstration about the proof of infinite limit and the limit at infinity. Okay, so we will continue this discussion in the next video. Try to unify all these representations, all these definitions of limits, different types of limit. Okay, we will stop this video and continue in the next one. Thank you.